everyone. What we're going to be doing today. Oh, Tess, say something. In it.
Testing 1, 2, 3.
Perfect. Okay. It just felt very quiet in my earphones, so I was thinking maybe half the thing's not working. Okay, we're good. Well, good morning, everyone. As promised, we're going to finish the mean value theorem off. I've got a little list to remind myself what questions I'm going to do. We're going to do a Rolle's theorem, a couple of examples of the mean value theorem, and then a little puzzle question, which is the last one. This one here is my version of it. So let's jump right in. The first one is similar to question 6. So we're going to be doing a Rolle's theorem, which is evidently this guy. Let me check. I may have written the wrong values down there. It looks slightly weird. Hold that thought for a few seconds. Where the heck are you? Not that one. Okay, question 6. X cubed, gotcha. Oh, it was, okay. Somehow, I must have been looking at half of one question. So what I have here is x cubed, take away 3x plus 9, and the interval is -2. Now, where the heck is my mean value theorem question that I was watching? Third time lucky. I think one of the problems is that in WebAssign it revamps the question each time you go in. So when I went back in, it had changed. There. Okay. Okay, so this is a cubic. We're being asked to find the magic value of C that has the property that f dashed of C equals 0. When it's Rolle's theorem, you're always looking for when is the function equal to 0. Oh, I see what's happened. I missed the -16x, that's what we did. So is it continuous? Check. Is it differentiable? Yeah. Why? Because all polynomials are differentiable. All polynomials are continuous on their domain. I'm going to cheat. Can you pretend f of 4 and f of -4 are both the same number? I'm sure they are. So all I need to do in Rolle's theorem is first find the derivative, which I believe is that guy, and then solve for 0. And not the prettiest thing to factor. So I'm looking for, looks to me like I'm looking for a 4 and a 4. And it makes that is negative and that's plus 0. Okay, I got it. So we are looking at when is this derivative 0? Well, if I factor it, I'm able to solve it relatively quickly. One of the choices is x equals 4, which just makes it so I can use it. And the other choice is, looks like, what would that be, -4/3. And that's it. You would write down the magic values of C, which are these two guys. Call it good. I'm a little bit dubious on the 4 because you may not be able to use the endpoint, but it's either both of these numbers or that one. If I had got, say, a -10 as an answer, I would have kicked it out because it's not in the limit. If I had got x equals 7, I would have kicked it out because it's not equal to the limit. I'm not 100% sure whether 4 makes it or not because the boundaries sometimes cause problems. But as I say, plug that in if it doesn't work, plug that one in. If it ends up only being that one, then boundary points, which means the start and finish, don't count. And that's basically Rolle's theorem, right? Take your guy, differentiate him, and there's guaranteed to be at least 1 point, if not more, in this interval. which will have a zero derivative. Now, in the mean value theorem, you have a little bit more to get, but essentially, there's guaranteed to be a value of C that has the property that its derivative is equal to this number. So, let's start with f of x is the natural log of x, and you are looking at the interval from 1 to 9. So that's your A and that's your B. For these functions, you only need to prove two things. Is this function continuous, at least for x between 1 and 9? The answer is yes, it'd just be a boring curve. Is it differentiable? Yes, it's the same boring curve. Take that for granted. What we then have to do is, I would find this guy here first. So we're going to find out what number, because it will be a number, this is. So in our case, it's going to be the function at 9, take away the value of the function at 1, over 9, take away 1. That guy 9, here we go, is going to be the log of 9, take away the log of 1, over 8. The natural log of 1 is 0, leave that guy alone. And so we now have a rather ugly guy to deal with. According to the mean value theorem, then you should be able to solve for a value of x in this range, and that value of x is going to be called c when we get it in this range, where the derivative is equal to that guy. Now, since the function is log x, its derivative is 1 over x. And that's the equation that I'm going to end up having to solve. So when you do a mean value theorem, just like when you do Rolle's theorem, the end is going to be here. You got to solve this equation. And, you know, it depends what you've got, how you're going to approach it, right? If it's a quadratic, I'm probably going to factor it, right? Once I move the number across. If it's, you know, a fraction, I'm going to do cross multiply, whatever. This one here, I think, lends itself to the cross multiply technique. Would you agree? So, natural log of 9 times x is 8. So 8 is actually that guy. And that is the fellow that they're wanting to find. And I don't need to, but if I wanted to, I would find the value of that. And I bet you that is somewhere between 1 and 9. Because mean value theorem says you're guaranteed to get at least 1, and that's it. If I solve whatever the equation ends up being, and there's 2 or 3 choices you might get, do a little check for each one. If it's in the interval, keep it. If it's outside the interval, cross it off, and only keep the ones that are usable. Are we okay with that process? Here's a function. Evaluate this expression as a number, and then solve when is the derivative equal to that number. Next one is we have a function e to the negative 2x, and we're being asked to use the mean value theorem in the interval 0 to 1. I know that e to the negative 2x is continuous. It's basically just a curve that looks like that, and it's differentiable, so we can use the mean value theorem. That's going to be my a and my b, so I'm going to find what the derivative is going to be equal to. I'm going to find that guy. I just like doing this guy separate, away from the derivatives. Just, I don't know, it just makes things simpler for my brain. Right, f of 1 would be e to the negative 2. F of 0 would be e to the 0 over 1. e to the power of 0 is also 1. A fraction over 1 is just a guy. So that's what the derivative should equal. So here is its function. Its derivative is a baby chain rule. It's e to the negative 2x times the derivative of negative 2x, which is negative 2, and that's going to equal this fella, which is equal to that. So what we are going to be looking at is solving that. And we're going to try our darndest to do an exact value. Now, I could simply just, I don't know, plug it in Desmos and see when does a curve y equal that, meet up with a horizontal line equal to that, and it would tell me, 0.12345. I don't want that. We want an exact value, which makes things more difficult, but still doable. In this case, I'm going to do, as long as you do it to both sides, it's okay rule. So I'm going to divide both sides by negative 2. Any takers for what I should do next? What should I do to both sides next?
Natural log.
Yeah. And if you take the natural log, nobody says the answer has to be pretty, right? It just has to be an exact answer. Okay, we're pretty close to the final result then. What will x be? What would I do to both sides to get x?
Divide by -2.
Right. Would you agree that that is not even vaguely elegant? Would you agree that's just one ugly mess? But isn't it also the exact value, which is what we're after? Now, in this case, if you wanted to, you could do something like this. You could make that the natural log of this guy. When you divide, you take away the other one. I wouldn't even do it. I was seeing if I could maybe make it look pretty, but I can't. So in my question, that would be the C value.
Hey, Professor, I got a question.
Yes.
So when you went from f of x equals e to the negative 2x, and you took the prime of that, how do you go from that to negative? I mean, I get how you get the -2 times e to the negative 2x, but how does that become e to the negative 2 minus 1?
The reason it becomes that is because of it's equal to that guy. So this bit here is basically f dash x, and this bit here is f of b take away f of a over b minus a.
Oh,
So
okay, now I understand.
That's equal to that, and this is the other side. I just separate them out because I think it's less work. I mean, you could do them side by side if you wanted to, I guess. Just an ugly answer. I don't like ugly answers. But I guess WebAssign, because it generates random things, doesn't always give you pretty answers because of that. Now, this is the last one, which is kind of fun. I'll just rewrite it all. You're told that the value of the function at 2 is 9. You're told that the derivative of the function is always greater than or equal to 2, at least for x's in the range 2 to 5. So that's what they tell you. And you're being asked to find the smallest value for f of 5. Now, superficially, that looks impossible because I have no function. I don't know what f of x is. So how am I going to be able to find what the smallest value is? But the mean value you can get is through this. we're assuming that this function is continuous and differentiable in the range 2 to 5. Now, the way that they've written that, couldn't I also write it like that? Wouldn't that be the same thing? And that means that this guy is A and this guy is B. So I'm going to find as much as I can of this piece, right? The mean value theorem, what it's equal to, right? That piece. And we know that f dashed of x, right, is bound to equal that at least in one value, right? Now, f of b, I do not know. Oops. F of 5, I do not know. Take away f of 2 over 5, take away 2. F of 5, I do not know. F of 2 is 9, and this thing is over 3. So according to the mean value theorem, there's some value of x, x equals c, that is going to equal this fraction. So far, so good. Now, since the derivative of some number is equal to that, and the derivative is always going to be greater than or equal to 2, doesn't that mean that this has to be greater than or equal to 2 as well? Does the logic of that make sense? Right? The derivative of the function is equal to this number at least one point. Since the derivative is always greater than or equal to 2, that means this number has to be greater than or equal to 2. So that's where we are. I now have set up a relationship. Now, if I multiply both sides by 3, and because it's a positive number, I'm allowed to do that. And if I then add 9 to both sides, isn't the smallest value for f of 5 15? Because everything else is bigger than that, right? So the smallest value for 5 has to be 15, and we've answered the question. What is the smallest possible value for f of 5? And the answer is 50. Do you like that puzzle question? Does it feel the way I've solved it makes sense? There is only one of those, but you'll get a version of that with your own numbers. Right, any questions about mean value or Rolle's theorem before we move on to our next guy?
When we type the answer for that question into
Mhm.
WebAssign, is it
Yes.
just going to ask for 15, or are we going to have to write it as f of 5 is greater than or equal to the number?
I'm looking at the answer right now, and so you would type in just 15 into the box, because the way WebAssign asks you to do it, it looks, this is what I'm saying in front of me. It has a box at that, and you just put 15.
Okay.
So that's the way it's going to, that's the way, whoops, I put X there. Yeah, but it's still 15 that you're writing. At least for my numbers, your numbers may be different. Anything else, or are we good to move on? Right, okay. Our next topic. Section 4.2. Not 4.2, we just did 4.2. Our next topic is 4.3. We're going to look at how do derivatives help you find out things to do with the shape of a function. And these are the kinds of things we are talking about. How do you use calculus derivatives to find the values of intervals of x where the function is increasing and decreasing, where the function is something called concave up or concave down? And lastly, how do you use derivatives to find local max, local mins, and coordinates of things called points of inflection? So basically, it gives you a little bit, it shows you how calculus can help you a little bit in looking at the basic shape of a function, right? It goes up, it goes down, it curves, it has hills, it has valleys, you know, all those kind of things. And we can use calculus to do pretty much most of that. Of course, you could put it into Desmos and look, but this is us doing it in a much more algebraic and mathematical way. So, first thing we're going to do is introduce you to some notes. So, imagine we have a non-weird function, just a good old-fashioned, up and down curve, nothing going on, right? Kind of cubic curve, right? Something like that. And I'm going to have it start here and finish here. That's just to make life easy for me, but it could go on forever as well. So let's say this is -2. Let's say this guy here is x equals 1. And this guy here is x equals 5. Let's say up here, x equals 10, right? Just put in some key x values. Now, when we say that, better give it its name. When we have a function y equals f of x, when we say it's increasing, what we mean is as you travel from left to right, the function is going uphill. So would you agree that if I'm here to here, isn't the function increasing in that part of the graph, right? It's going uphill. So always think of traveling along from left to right, my little car story, right? If you're going uphill, it's increasing. So we tell people when something is increasing by telling its x coordinates, right? We don't care what the y values are. We just say that x from -2 to x equals 1, and the curve brackets mean you don't count the endpoints. So you don't really want to. You could argue that because this function starts at -2, I guess you could call that one an endpoint, but in general you don't call them, right? So -2 to 1. Would you agree that it's also increasing from 5 to the end of this curve? And what does that look like? Well, for values of x from 5, I guess I'll call the endpoint that guy. So for this function, for x's between -2 and 1, and from values of x from 5 to 10, the function is increasing. Let's look at decreasing then. A function is decreasing, right? As you travel from left to right, it's going downhill. So in this particular question, would you agree that the function is decreasing from 1 to 5? Are we good? No. Let's do another one. Should plan ahead, shouldn't I? Now, functions should have arrows at the end, at least that's the way I would write them, to indicate that they just continue forever in both directions. Now let's tell you that this guy here is at 2, this guy here is at 4, this guy here is at 6. So they're really the only numbers you need to look at, right? If you're talking about increasing and decreasing. So a function is increasing if, as you travel from left to right, you're going uphill. So would you agree that from 2 to 4, okay, that's a weird scale, but whatever. From 2 to 4. And then, it's also increasing from x equals 6 forever. If you want to continue forever, don't you have to put an infinity in? So that's what that would look like. This function is decreasing. Well, it's decreasing here As you travel from left to right, you're going downhill. So that's from negative infinity to 2. Union. And then a little baby decrease from 4 to 6. Are you comfortable then if someone shows you a graph that you could give me the interval of x's where it's increasing and the interval of x's where it's decreasing? You all feel comfortable about that? Right. So let's have a look at one of their questions and essentially just get some practice. I got a chat and then I should know. So let's get started. Right, here's the function. And it's got down here, find the interval or intervals in which it's increasing. And interval notation is those brackety things that I was doing, right? So if I look at this function here, would you agree it's increasing from 1 to 3, right? From x equals 1 to x equals 3. So we would write that down as a 1, 3 guy. And then from 4 to 6. And so I need to do union symbol, which is that guy. And then we'll do 4 to 6. And now I have a little bit of a problem. I'm assuming that this function starts at 0, x equals 0, and it finishes at x equals 6. If I'm assuming that, can't I put that down? Because 6 is the end of the line. So that's the only time I might use a square bracket. Okay, and I'm going to have to do something here. Hold on for a moment. I want to do something to check. So how am I going to do this? I'm going to do this as a student. That way I can have it check my answers. Because I want to find out whether it wants, you could argue curved or square. Right. So here's the guy. And intervals of its increasing is 1 to 3. So I'm just repeating my answer. Hit the sets button to get union. And then 46. So my first attempt is going to be that one. Curved brackets everywhere. Submit answer. Okay, it's taking curved brackets. I really want to find out square bracket. Okay, it's accepting both answers, which isn't helping. Well, I guess it is helping. Doesn't it mean you can put in one or the other and it won't matter? Now, if you want to find out when it's decreasing from x equals 0, which is here, and it finishes at 1. So that would be 0 to 1. And then it's also decreasing from x equals 3 to 4. And check that out. Okay, good. Now let's return to our notes now. Increasing and decreasing, I think are kind of intuitively make sense, right? Uphill is increase, down here is decreasing. Now we're going to look at something which is called concavity. Concavity is a term that basically is talking about how the shape of the curve is curving. Bad. Some curves have that kind of happy face shape. Some curves have a sad face, right? Concavity is what we are talking about. is the shape basically happy or is it sad? Now, when it's happy, we call that concave up. And when it's sad, we call it concave down. And I think they stick to the word words. So it's concave upwards, concave downwards. I just do concave up, concave down for short. And if you take any curve, any normal function that has curves in it, right? So it goes up, it goes down, it goes up, it goes down. Aren't there certain places where it's happy and certain places where it's sad? Right. So, would you agree that in this part of the world, isn't the curve part of a happy face and so it's concave upwards? Would you agree that at this point here, the curve is part of a sad face? So here it's concave up. Here it's concave down. Now, you notice there's a little blank gap right now in the middle. There won't be a blank gap. At any point on a curve, it's either part of a concave up or it's part of a concave down, right? It's not basically allowed to be, well, we don't know, which means that isn't there some indeterminate point, let's pretend it's there, where the concave down changes over to a concave up, right? You see that point now? That point has a name. It's called the point of inflection. Okay, are you comfortable what concave up means, right? Happy face, concave down. Now, if you look over here, this part of the curve, would you agree this here is also part of another concave down, right? Oh, by the way, if nothing is happening, everybody at the end belongs to the last thing that happens, right? So if it was concave down, it just keeps on concaving down. Now, in this case here, somewhere I'm going to put a guesstimate, right? We're going to have that inflection point, the changeover point from a happy to a sad, or from a sad to a happy, right? So if I put numbers in this, let's say this guy goes to 0. So 0, let's say that's 5, let's say that's 6, let's say that's 8, let's say that's 11, let's say that's at 13, and I know, goes on forever, right? Actually, let's have both sides go on forever. That's more interesting. If I was being asked for what values of x is the curve concave up, it would start at 6 and it would finish at 11. So all the values of x between 6 and 11 are when this function is concave up. If I said to you, when is it concave down? You're going to say anywhere in this region and anywhere in this region. So that's going to be what, negative infinity, because I'm saying it goes on forever, all the way to 6, and then starting at 11 and all the way to infinity. Have you noticed that the tops of the hills, that's at 5, at 8 and 13, have nothing to do with concave up and concave down? All you need to know is the inflection points, right? Where does the changeover happen? And sometimes you have to make a kind of intelligent guess. It's easy to tell, isn't it, when you have a top of a hill or a bottom of a valley, right? It's pretty easy to tell what they are. It's much more difficult to pick that point, right? Because it could be a bit lower, right? And it might be probably not, but it might be a bit higher, right? This one could be a bit lower, might be there, might be a bit higher. So there will be a little bit of guessing. I tend to go for the obvious and hopefully that's the one they're looking for. And it probably will be. Yes.
Professor, I do have a question. So
Mhm.
for the last question, for decreasing the interval was from negative infinity.
Yes.
How come on concavity it's the direction is opposite? Because on the last one it was positive. It looked like the line was going up. Or is it just because we're going from left to right? But
Going from left to right, I think, is what your confusion is. I mean, yeah, this red bit, right? This whole red bit going on forever, right away down here. This whole bit is all part of a concave down. Right? So if you're traveling from left to right, you see how you're part of a concave down. And over here, aren't you also part of a concave down? I'm not sure if I've answered your question.
I guess I understand it's still for the concavity. It's just
Right.
for the interval notation for concave down, it starts with negative infinity because it's going down.
Yeah, this is going forever. So that means the x
Mhm.
value is going to be negative infinity.
Okay, but then on the last one, do we just
Yeah.
always no the last question for the interval notation for decreasing we went negative infinity, comma 2.
Yeah.
I guess on concavity, I guess my question is for concavity, do we just go off what the graph looks like while on the other one we go with left to right?
Yeah, left to right is much better for increasing and decreasing. And concavity, it's much more to do with happy face, sad face. So you don't need a left to right. Would you agree a happy face is happy no matter where you put it?
Mm-hmm.
A sad face is sad. Yeah. So I would think that would be the good way. So think about traveling from left to right. When you're talking about increasing and decreasing, that's quite helpful, isn't it? Up and down. Right, going uphill, going downhill. When you're thinking concavity, think of shape, happy face, sad face. That's
Okay,
how
all
I
right,
would
thank you.
say it. Right, let's,
Professor, can I say something that I was confused with?
yes?
So those intervals are only dealing with the x values and don't indicate the direction of the graph, like the value of the graph. So when
They,
you're
yeah,
closing
they're
it,
only x coordinates.
yeah, when you're closing it with the positive infinity, we're talking about the x values only and not the direction of the graph. I'm not sure if that helps or not, but I was really
Yes.
Okay, yeah, that helps.
That's what I'm talking about. I'm talking about, it goes 17, 18. The x coordinates are going to infinity. Right? So it's not to do with its y coordinates. In fact, neither of these things care what the y coordinates are. It's all about what the x coordinates are.
Oh, okay, no, that helps a lot. Thank you.
Thank you. That was helpful as well. So let's do an example. Right, back to this guy. Now, we already did the increase and decreasing. Let's look at concavity now. Okay, it looks like this question starts at x equals 0 and finishes at 6, right? That's nice to know, right? Okay, so would you agree there's a happy face from x equals 0 here? Would you agree it's a happy face going on? And would you agree that there's a sad face taking over from roughly x equals 2 to 4? Would you agree that is pretty clearly a concave down now? Now, so if I wanted to tell people when it's concave up, wouldn't I be saying from x equals, it's all about the x's, from x equals 0 to, would it be reasonable that the changeover happens at x equals 2? That's a nice whole number. So I would go here and I'd say, oh, and they tell you open interval, so that explains why from 0 to 2. Now, I'm going to look at this shape and I can't see any more happy faces, right? There's nothing got that big happy you smiley face thing. You look at this guy, doesn't it go from x equals 2 to x equals 4? Would you agree that's a concave down shape? Right? From x equals 2 to x equals 4. So 2, 4. And then I'm going to do union. And the reason I'm doing union is from 4 to 6. Do you see the last piece of the curve? Every part of a curve is either going to be concave up or concave down, with the one exception: if it's a straight line, it's basically neither. But you're not going to deal with straight lines, so we can pretend they don't exist for this question. Would you agree that it ever so slightly isn't that eventually going to be part of a sad face? Can you imagine it's curving a little bit less each time? So this is a little bit harder to see. So with a little bit of imagination, can you see it's part of a sad face? And that means from 46 as well. And open intervals just means you can't use the endpoints. And you might think, why I didn't just do start at 2, right, and finish at 6. And that's because something really horrible happened at x equals 4. Do you see one of those corners, the cusps as they're called? At that point there, doesn't the derivative not exist? And we will be finding increasing, decreasing, concave up and concave down, all with calculus. And what calculus says is, if you don't have a derivative, you can't be part of a concave up or a concave down, right? You're a zero concavity point, right? You're just a nothing point. And that can happen. Now, would you agree that there's a point of inflection? Oops. A changeover. That's what a point of inflection is. At x equals 2 and another one at 4. So find the coordinates of points of inflection. So the key word here is coordinates. So I'm going to write something down that looks like an interval, because that actually doesn't look like a coordinate, but it actually is representing an interval. Right? It's representing all the values of x from 2 to 4, and then it's representing an interval, all the values from 4 to 6. But we're now going to do coordinates. So I'm emphasizing this is a coordinate. Right. Would you agree at x equals 2, there's a changeover? That's a point of inflection. And the coordinates of that is 2, 3. I can't say this often enough. The coordinates, a single point in space, is 2, 3. That does not mean the interval from 2 to 3, doesn't it? Just mean a single point, coordinates 2, 3, right? And then I'll do a comma, because, well, maybe I won't.
When I did it, it only accepts 2, 3.
Okay, good. So let's look at this weird one, 4, 1. 4, 1 is not going to be called a point of inflection. I mean, and why is it not a point of inflection? A changeover has to happen, right? A concave up must turn into a concave down for that place to be called a point of inflection. Would you agree at x equals 4, a concave down just changes into a different looking concave down? But it starts at a concave in either side, right? It's not a changeover from one to the other, isn't it? Just a concave down turning into a different concave down, right? It's not changing. And that's why that guy's not there. Now, if they had put in a question like, give me the coordinates of a cusp, wouldn't you then put in 4, 1, right? It does have a name, but its name is not a point of inflection. That was good. Right, here's another one. Okay, give me any interval of x's where this function is increasing.
Zero to 1.
Agreed. Would you agree it's going uphill? So from left to right, right, increasing and decreasing, right? From left to right, am I going uphill? Would you agree from 0 to 1 it's uphill? Increasing. Is there somewhere else that it's increasing? Because there is.
And then would it be
4?
3?
I hear 3 to 4. Do you want to change it a little bit? From 3 to where?
Would it be infinity?
Not yet. Well, no, it's the short answer, but I understand why you're saying it. It's going to go from 3 to 5. And then it's going to go from 5 to infinity. Now, why is it not going from 3 to infinity, which is what I think Matthew was getting at?
Is that because of the
Isn't-
point of inflection?
There is a point of inflection at 5, isn't there? But isn't there also a horizontal tangent line at 5, which is more the reason? Right. So have you noticed that increasing turns into decreasing normally when there's a horizontal tangent line, right? A zero derivative. Now, if I was talking about decreasing, how about from 1 to 3, which is actually the only part of this curve that is decreasing? Now, judgment call time. Would you agree that if you were talking about concave up, it would be from 0 to 2? And then that's concave down, I should say, from 0 to 2, and concave up from 2 to 4. And so there'd be a point of inflection right there at x equals 2. Right, so there's a changeover from a concave down turning into a concave up. There is another point of inflection, and it's not at 5. 5 is just a zero derivative. But there is another point of inflection over here where a happy face and a sad face change over. What's the x coordinate of the point of inflection on this shape?
4,3.
Yeah, there's a 4,3. Do you agree? Now, what's happening from 4 to, let's do it. Would you agree from 0 to 2, concave down? From 2 to 4, concave up. Now it gets a little bit messy. From 4 to what number is it now another part of a concave down? From 4 to what other value of x is it part of a concave down? Now you don't need to see both sides of a happy face or a sad face to be concave, right? You can have just one, you know, the left half part or the right half part. Okay,
45.
45. And then what's going to happen from 5 to 7, I guess that is. What's happening at the last piece? Concave up
It's
or concave
concave up.
down? Concave up. So do you see how this shape basically goes? Concave down, concave up, a little baby concave down, and finishes with a concave up. So that makes 3 points of inflection. A point of inflection at coordinates 2, 2. A point of inflection there, coordinates 4, 3. And lastly, a point of inflection here at 5, 4. How are we doing? Are we increasing and decreasing? I don't think most people have a problem with, right? It's pretty, you know, left to right going uphill. I think concavity sometimes is a little bit harder to visualize. How are we doing with concavity? Feeling good? Good. I'm good. Feel good. These are not concavity questions, so let me just leave this. Right, moving on. I tell you a little property where derivatives kick in. A function y equals f of x is increasing when its derivative is greater than 0, and it's decreasing when its derivative is less than 0. Does that make sense that if the derivative is positive, it's part of an increase, and when its derivative is negative, it's part of a decrease? So if I was talking about this guy here, right, where my finger is, isn't that derivative pointing upwards? That's increasing. If I pick this bit here, won't it be decreasing? Now, what that's going to allow us to do is that is going to allow us to find when is a function in increasing and when is it decreasing? Because doesn't that just become when is the derivative positive? That's it's increasing. And for what values of x is its derivative negative? That's going to be decreasing. So we can now use calculus instead of having to have a picture in front of us. That's kind of nice. Okay. Now, suppose I give you a graph not of the original function, but I give you a graph of the derivative function. And I tell you that the graph, let's say, looks like that. So this is the graph of the derivative function. And I'm going to have to put in some numbers here because they're going to be useful. Let's suppose this is x equals -2. Let's say that guy is x equals 1. Let's say that's x equals 3. Make that x equals 5. I'll make that 7. And we'll just have the graph go on forever, right? So if you give me a graph of what the derivative of a function looks like, this is one I've gave you here, you can actually tell when is it increasing and when is it decreasing. The derivative will be positive when the graph is above the x-axis, and won't the derivative be negative when it's below the x-axis? So if you are asking me for what values of x is f of x increasing, I can say, well, anywhere that way, which you agree the curve is below the line, so that would be from -infinity to x is -2, and here forever. Are you comfortable about how this graph allows me to easily tell when a function is increasing and when it's decreasing? It's, I just got that back to front, didn't I? There we go. And a function is decreasing when its derivative is negative. And now I can do the one I thought I was doing. This function will be increasing, essentially, for any value of x between here all the way to here. And why? Well, if the curve is positive, which it is here, doesn't that make the derivative positive? And the derivative positive means it's increasing. So that would be from -2 to 7.
So you said that when the derivative is positive, it's increasing.
Yeah.
Okay.
Yep. Now, concavity. Ooh, that's a little bit harder. But you can actually find when is a curve in concave up and when is a curve concave down. God, it's a tongue twister, right? When is it concave up and when is it concave down from the derivative graph? Now, when it was the original function was a little bit of guesstimation at when the transfer happened, right? You know, did it happen here or a little bit lower, a little bit higher? It's not that difficult when you have a derivative curve. You just need to know these guys. Because these fellas are the points of inflection. So I know this shape is going to change at 1, then it's going to change at 3, and then it's going to change at 5. And at least I could tell, excuse me, I could tell you the x coordinates of the points of inflection. I would have a harder time figuring out, is it concave up then turning into concave down? So what we would do instead, if we wanted to do it only from a graph, is if the first derivative tells you increasing and decreasing, the second derivative tells you concave up and concave down. Let's see how that works. Can you imagine a different curve, right? And this is a curve of a different function. I'm making no attempt to say it's this guy, right? And I'm going to tell you that that happens to be at 1, that happens to be at 5, and that happens to be at 7. A function is concave up when the second derivative is something, and the function is going to be concaved down when the second derivative is equal to something. So increasing first derivative will be positive, decreasing the first derivative will be negative. Concave up, what do you think the second derivative is going to be?
Greater than 0.
Now, isn't that nice? Concave up is positive second derivative, concave down is negative second derivative. So we can find out increasing and decreasing from here. And we can kind of get points of inflection, but that's as much as you want. But really should use this just for increasing and decreasing. And if you have a graph of the second derivative, can't you use it to find concave up and concave down? So let's try this. See if we can answer that. Using only this graph, isn't it going to be concave up when you're there? And when you pick values from there, would you agree in both those regions, the function is above the x-axis and so it's positive? So it's going to be concave up for values of x from negative infinity to 1 and from 5 to 7. And then it's going to be concave down. I don't know what kind of how to do dotted lines. It's going to be concave down from 1 to 5 and 7 forever. So for values of x from 1 to 5 and from 7 to infinity. I'm going to call them PI for now. The x coordinates of points of inflection, you can get those from here as well. The x coordinate of a point of inflection you can get from this graph. So a point of inflection is where a concave up turns into a concave down, right? Or vice versa, right? It changes from one to the other. Give me the x coordinate.
I've got a question on what you just had about the concave up and concave down.
Yes.
So you have it as concave up from negative infinity to 1.
Mm-hmm.
Why is it not concave up from 1 to 5?
Because you're looking at that and seeing a happy face, aren't you? That's why you're thinking it's concave up.
Yeah, exactly.
Right. But it's to do with the value of the second derivative, not to do with the shape of the second derivative curve. It's to do with the value of it. In other words, when you are positive, right, when the second derivative is above the x-axis, your second derivative is a positive value. And that's where the concave up is now happening. It's happening because this is positive and that's positive. It's not to do with the shape. The shape is when you've got f of x in front of you, right? If you've got the original y equals f of x, Then you would look at happy face and sad face. In these,
Oh.
aren't you looking at the value of the function? So I'm looking at the value of the second derivative function.
So concavity has to do with the actual function, not the prime of the function then, correct?
Correct. Yeah, because you could look at this guy and say, why is it not concave down and concave up? Well, this is the graph of the first derivative. The shape of the first derivative tells you nothing about concavity. The shape of the second derivative tells you nothing about concavity. Isn't it the value of it, right? If it's positive or negative, that tells you. Okay, so for this function, tell me the x-coordinate of a point of inflection. There's 3 of them.
1, 5, and 7.
Have you noticed that those are going to be when the second derivative is 0? Now, if we went over here, if I went and said to you, do you notice that the point -2 and 7 were quite important? Because when they concave, no, they're increasing, got to get my language right. Wasn't the function increasing from -2 to 7? You see that? And then wasn't it decreasing 7 onwards and -2 beyond? Are we good? Right, let's do practice. Practice makes perfect. So we are now looking at a first derivative. Right, in this first derivative function, they've got a solid dot at the start and a solid dot at the finish. That tells me no infinities, right? None of my answers are going to have infinity in them. If they want to know on what intervals is this function increasing, wouldn't it be from 0 to 1 would be the first interval. And then I'll do union. Now, where else is this function increasing? Remember, what you're looking at here is the derivative function, right? Not the original, but what the derivative looks like. Where else is it increasing?
3 to
Right.
5.
Okay. That makes sense, guys. It's what positive means increasing, right? Negative values below the x-axis means decreasing. So if I was looking at this fella, would you agree that from 1 to 3, so for x from 1 to 3, it's decreasing, and what, from 5 to 6 as well? That makes sense? First derivatives tell you all about increasing and decreasing. I'll skip that for a minute. Here is a, pardon me, here is a second derivative. Is it a second derivative? Not still a first derivative. They're not going to show you a second derivative, that's fine. Right, so this one is, when is it increasing, when is it decreasing? Would you agree that it's increasing from x equals 1 to 4? And then a little, forget that guy, and then 5 to 6. And then it's decreasing from x value 0 to 1, and then a little baby from 4 to 5. Above the axis increasing, below the axis decreasing. And that's essentially what the first derivative graph can tell us. The first derivative graph can also tell us one more thing. Wouldn't it be nice if we could look at the derivative functions graph, right? And tell, is there a local max or a local min happening, right? And the answer is you can do that. Let me put in a graph. Goes down, goes up. Yeah, that'll do. And this is what the derivative function looks like. And I'm going to put that in as -2. That guy's going to be 3. That guy's going to be 5. Now, if I asked you when is it increasing, when is it decreasing, we know how to do that, right? So I'm skipping by that. I'm going to look at this graph and I'm now going to try and find out where the local max and mins are. And secondly, is it a local max or a local min at that point? So the first thing is, where do you find local max and mins? Well, a local maximum or minimum will always occur, typically, when the derivative is 0. Now let's think of why that would happen. If you imagine the normal curve, right, of y equals f of x, if you want to know where the local max and mins occur, don't they happen when the derivative is 0? Does that make sense why that's true? Now, I can look at this graph and it's pretty easy to tell. Would you agree that there are 3 places where the derivative is 0, right? X equals -2, x equals 3, and finally x equals 5. So I know where they are. They're going to happen at x equals -2. They're going to be a max or a min, a local max or min, x equals 3, and finally one at x equals 5. So the next piece of the puzzle is, how do I tell what I've got? Have I got a local max? Have I got a local min? Have I got what's sometimes called a horizontal point of inflection? We all know what local max looks like, agreed? And we all know what local mins look like. There is a third possibility. You don't get it very often, but do you know x cube's an example of it? Can't you have a 0 derivative and it's not a max or a min? It's called a horizontal point of inflection. So that could happen. So we have to be aware of it. So let me show you how you do it. Focus on this point here for a minute at x equals -2. If you choose a value of x slightly to the left of it, like -3, would you agree the derivative is positive? And if you choose a value to the right of it, would you agree in this case, the derivative is negative? So I want you to imagine that we focused in just at -2. If the derivative is positive, doesn't that mean the curve's going up the way? And then its derivative is 0, so doesn't that mean it's horizontal? And then the derivative is negative. Can you see that combination generates a local max? Positive derivative, 0 derivative, negative derivative, right? Positive, 0, negative. So I know there's a local max there. Let's look at 3, right? Forget what's going on here. If you choose a value of x a little bit less than 3, would you agree the derivative is negative? And if you choose something a little bit bigger than 3, would you agree it's positive? Now, what does that mean, right? Negative means it's coming down the way, decreasing. Then it's 0, and then positive means it's increasing. Well, that means there's a local minimum happening here. We did this one, local max. We did this combination, local min. Okay, one more to go. What's happening at 5? Right? If you choose a value of x slightly to the left, would you agree the derivative is positive of the x's? If you choose one a little bit more, would you agree the derivative is negative? What does that look like? Local max or local min in the original function. So it's increasing, 0, and then negative.
Be a max.
Right? Increasing, 0, and negative. So you got a local max. Do you see how the derivative function, which is what this is, not the original, this is the derivative function. Doesn't it tell you an awful lot about the original function? It tells you when it's increasing, it tells you when it's decreasing. Doesn't it also tell you the x coordinates where local max and mins are happening? Now, if you wanted to see a kind of unusual, because it doesn't happen very often, what a horizontal point of inflection might look like, imagine I had this one. So this is at x equals -3, and let's say this is at x equals 4. And we're talking about looking at the derivative function. Right, do you see this guy here at x equals 4? This is going to be a horizontal point of inflection. Let's see what that looks like. Would you agree slightly less and slightly more? Aren't they both positives? Right, they're both of the axis. Now, if you go positive, 0 and positive, do you see that horizontal point of inflection shift? So you pretty much know, if you tell me the derivative function, right, if you show me that guy, you pretty much know when it's increasing, when it's decreasing, local maxes, local mins, and horizontal points of inflection. That's a lot of information contained inside just a derivative function. Any questions? Are we good? Let's see what we can find. Okay, try this one. It's got an awful lot of bumps in it, which is a little bit. Come on, there we go. Maybe make this a little bit bigger. Here we go. This is the derivative function, right? Yet we're going to answer all sorts of questions about the original function, right? The f of x guy. For instance, looking at this function, starting at x equals 0, give me an interval when the function's increasing.
0 to 4,
And give me the other place where it's increasing.
6 to 8.
Right, you comfortable? You can look at that until increasing, right? Now decreasing would be what, from 4 to 6? And my best guess is, would you agree it looks like that curve just goes on forever to the right-hand side? So how about 8 to infinity for decreasing as well? In this curve, tell me the x coordinates of max, min, local max and local mins. The x coordinate of where local max and local mins will happen.
4 and 8 would be max, 6 would be min.
Well, you got the whole package, yes. At 4 and 6 and 8, isn't that where the local max and mins will happen? Right. Horizontal points of inflection have that special case, don't they? Just bounce off the x-axis. So you'll know them when you see them, right? So these are clearly that. Let's pick one of the ones he just said. Let's look at 6. Would you agree it's negative on the left of 6, but positive on the right? So that would be going downhill, 0, going uphill. That's a local min. What else? That's what these questions. Oh, concave up. That's going to be trickier. Because if I want to do concave up, really shouldn't I have a second derivative function in front of me? You agree? Because isn't concave up positive second derivative and concave down is negative second derivative? Agreed? So there are two ways to approach this. The first way is just looking at the guy in front of you. I can tell where points of inflections are going to happen, and there are going to be a lot of these darn things. There is going to be a point of inflection at x equals 1, at x equals 2, at x equals 3, at x equals 5, and finally at x equals 7. How do I know that there's one at 1, 2, 3, 5, and 7?
Horizontal.
Horizontal tangent line, right? If you find a horizontal first derivative, doesn't that mean the second derivative 0 there, right? The derivative of a derivative. And that will work, but then you have to figure out, is it concave up or concave down? And that's not that obvious looking at the first derivative. So I suggest that we do it this way, which is going to be pretty much the last thing for today, is that we try as best we can to draw what the second derivative would look like. So to be able to do that, I need to start with the first derivative. So it goes, I don't need to be too, precise. Yeah, can you pretend that's pretty much the first derivative that we got, right? I'm not being too precise. I am going to be very careful about here, 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 and here, right? The 4 places that we mentioned. And I'm going to deliberately drop a vertical line and tell you that that happens at 1. Then another one through this 0 guy, and that happens at 2. Another one here, which happens at 3. 4th one here, that happens at 5. And there's one over here, I almost missed it. And the last one here, and that's going to happen at 7. What I'm now going to draw, because we've just got the first derivative, is I'm now going to try and draw what the second derivative looks like. Can you remember those questions that we did where they showed you a graph and they asked you to sketch its derivative? Remember those guys? This is the same thing. Instead of this is f of x and I'm now going to draw f dashed of x, this is f dashed of x and I'm now going to draw the second derivative of x, but the process is the same. Now, in this story, I'm going to call them, call them region A, B, C, D, E, and F. There's going to be a lot of regions. In region A, first, as you drop down there, aren't these guys all zeros? Right, so they're all going to cross the x-axis. That means their derivative is 0. Right, in region A, would you agree the answer is positive? And would you agree the derivative in region B is negative? In C, isn't it pointing up the way, so it's positive? In region D, everybody's pointing down the way, so it's negative. In E, they're pointing up the way. And in F, they're pointing down the way. So there's 1, there's 2, there's 3, there's 5, there's 7. And can't I just basically do this? And it doesn't matter how high or low I go. Haven't I now got a pretty crude but usable sketch of the second derivative? Now from that guy, isn't it a lot easier to now tell concave up, concave down? For instance, from 0 to 1, isn't it concave up? From 1 to 2, it's concave down. So I'll just put them up, right? Up, up, up. And from 1 to 2, down, down, down. So if you had to tell me when is this function going to be concave up for what values of x, you would say from 0 to 1, and then from 2 to 3, and then from 5 to 7. Are you comfortable with that? Positive second derivative, positive second derivative, positive second derivative, right? And if you notice, I'm not paying any attention to the shape. Isn't it all about positive or negativeness? Positive concave up, negative concave down. And as an added bonus, don't I now know points of inflection at x equals 1, 2, 3, 5, and 7? And that's just an easier way, I think, in dealing with the concave up, concave down question, right? And points of inflection. How are we doing, guys? Right. We haven't really done any calculus yet, so we have time. That's nice and visual, which is cool, but wouldn't it be just so much easier if we could do all these things more algebraically and less drawing pictures and shading things in? So here is a nice polynomial function. And I'm going to show you for this one question, because that's the only one I'm going to do, how to find everything you could possibly want. That means intervals of increasing and decreasing, location of local max and mins, intervals of concave up and concave down, and coordinates of points of inflection. I mean, if you knew all those things I just mentioned, couldn't you draw a really good sketch of this guy? Now, I know it's an X cube. Doesn't X cubes kind of look like that? So already sort of I know what should happen. Let's see how it works. First thing I'm going to do is find the first derivative. And the reason I'm going to find the first derivative is this guy, this function, is going to tell me everything I need to know about increasing, decreasing, local max and mins, right? And horizontal points of inflection if they have. So that's basically step one. Find the derivative. Step two, find the critical numbers. So we are going to find places where the derivative is 0 and places where the derivative, the first derivative, is undefined. So I'm going to solve when the first derivative, which is this guy, is 0. Okay, we're going to get exact values, so it's a good idea to get used to factoring things because you're going to do a lot of that in these questions. Looking at that, is there anything you could do that might make solving equals 0 easier? Okay, any factoring?
Factor out the 3.
I would.
And that's going to give you x minus 4 times x minus 2.
And what we have just found then are the only two critical numbers for this function. Would you agree there's no place where it's undefined, so I'm not going to look for it. Right. Well, that's great, but that's only step 2. We haven't done enough yet to identify when is it increasing or decreasing. So this is where step 3 comes in, and it's create a table of values using what we call test points. I'll show you how that works. You draw a number line representing the x coordinates. And in this case, I'm interested in 2 and 4, so I'll probably start maybe over here, 0, 1, 2, 3, 4, at least. So make sure your number line has 2 and 4 in it and a few spare. Now, this number line is going to, I guess it's called a table of values because in most books they make this a table. I make it a number line. So I guess if I was calling it something, I would call it create a number line of values. But well, that's what it's called. I know that at x equals 4, the derivative is 0. And I know that at x equals 2, the derivative is 0. And just to remind us all, I'll even put a little f dash of x up there so that we know that this is talking about the derivative values, not the original function's values. Now, what's these things called? Test points. I want you to imagine that these two critical numbers are essentially separating the graph of the derivative into 3 chunks. You pick a number in each of these as your test point. So in this region here, I could pick -1, I could pick 0, I could pick 1. I could even pick 1.234, but nobody in their right mind would pick that because it's too hard to calculate. So choose an x coordinate, any value you like. I'm picking 0. So that's my first test point. And I'm going to find the value of the derivative at 0. This function here, where are we, is probably the best one to use. So it's 3 lots of nothing, take away 18 lots of nothing, plus 24. And so the answer is 24. And I'm not really too concerned about the number. I'm really only concerned that it's positive. So you put a plus there. And then you put a plus everywhere in that region. And you might say, well, you only put that number. How can you tell me that all these other places that I might have chosen are also positive? And the argue goes something like this. This function is continuous and differentiable, right? That means it can't jump from one side to the other. It's smooth curve. If this was positive turning into negative somewhere, wouldn't it have to go through a 0 to do that? There are no more zeros, right? These are the only 2 zeros in town, so it's impossible. So the logic says, once you found the places where 0 are, if you find one test point is positive, everybody in that region is guaranteed to also be positive, right? The logic says it can't be a bit of one and then a bit of both. Who do you think I'm going to choose for my second region, this one here? What x coordinate for my test point? What will I pick?
3.
Yeah. Too silly a question to ask, but just thought I'd ask it. F of 3 is going to be 3 lots of 3 squared, that's 27. Take away 8 lots of 3, which is 54. Add a 24. That gets you 51. You get -3. Again, I'm only interested in the fact that it's negative, not that it happened to be 4 or 24. So everybody here is negative. Right, and for the last one, I'm picking 5. And 3 lots of 5 squared get me 75. 5 lots of that get me 90. Then I add 24. And I believe the answer is 9. So I know it's positive again. And so here I get positives. This table of signs can now be used to find the values of x where the function is increasing and the value of x where the function is decreasing. Well, aren't you increasing when the derivative is positive? So that means everybody here. So that would be, because it's going on forever, from x equals -infinity to 2. And then from 4 to infinity. And when is it decreasing? From 2 to 4. That's good. Now I can also use this guy. Oh God, this is going to be the finish right now. I can also use this guy to tell you whether there's a local minimum or maximum at x equals 2, and whether there's a local minimum or maximum at x equals 4. So here's the short version. Positive, 0, negative. Positive, increasing. 0, negative. Do you see a local maximum there? This one. Negative, then 0, then positive. Do you see a local minimum there? So you can also find from the table of signs that there's a local maximum at x equals 2, and that there's a local minimum at x equals 4. And if they wanted you to give the coordinates instead of just the x value, x equals 2 would be plugged into not the derivative, but the original function, right? We want to know its y coordinate. And so that would be 2, 4, 8. 8 take away 8, oh God in Himmel. 42 and 17, I just made up numbers to finish the question. You'll get the real values and you plug them in. And actually, don't we probably know enough to have a decent sketch of this function? couldn't I plot the local minimums coordinates, the local max, and then just do happy face, sad face thing? In fact, if you kind of shift them together, don't you get that cubic look that you do expect, right? Happy face, sad face. And sorry for keeping you, well, not quite over your time, but we only get 1 minute left. So last name, and bye-bye.